Oh, okay. So thank you for waiting. Let's start my talk. So today I will talk about normalization problem for deformed exponential family. So as in the previous talk, normalization is important in information geometry. So today I will consider the parametric case for this problem. So this is joint work with Scarfone and Wada. I think everyone knows this very fundamental property, but let us review. So we say that a statistical model S is an exponential family. So if the set of probability densities can be written in this form, so in this case, one connection is flat, and the natural parameter theta is an affine coordinate system. So, and the normalization function psi is a Hessian potential. So the second derivative determines the Fisher metric, and third derivative determines the Amari-Centos tensor field or the cubic form. And these structures makes a dual Fato space. But for exponential family, we can write many kind of forms. So we say that S sub E is an exponential family of E form or exponential form if all the arguments putting on the exponential inside the exponential function like this. And we say that S sub EM is an exponential family of M form or mixture form if there is a normalization function in front of the exponential function. This one. So for an ordinary exponential family, these normalizations are not important because we can interchange these forms. But however, in the case of deformed exponential family, these representations determine a different statistical model in general, as in the previous talk. So we would like to consider deformed case. And we say that S sub E is an exponential family of pure exponential form. So the normalization is only the function psi theta.
Excuse me, what is x? X is belonging to what?
X is a random variable. So random variable. So x is an argument on.
This is a member of Rn of R or some abstract space.
X is belonging on the sample space. So in this talk, we usually consider on R, but it depends on the formulation. So anyway.
The reference measure is a Lebesgue measure.
Of course, it depends on the assumption. In this talk, we usually consider Lebesgue measure, okay. But we can choose another measure. So this is easy but Gaussian distribution. So Gaussian distribution is an exponential family, and if we set parameter like this, then Gaussian distribution has pure exponential form. And the Fisher metric with respect to this coordinate is given in this form. So next, let us consider log Gaussian distribution. So log Gaussian distribution is given by this form. So if we put the parameter like this, then log Gaussian distribution can be written in this form. So this is an exponential family, but it is not a pure exponential form. but the Fisher metric coincides with the ordinary Gaussian case. Of course, by the variable change t equals log of x, so log Gaussian distribution reduces to the Gaussian distribution. So their structure must be coincide. This is one of the requirements of information geometry. So the metric, Fisher metric is independent of the choice of reference measure. So this is log Gaussian distribution, but we change affine coordinate like this. Then log Gaussian distribution can be written in pure exponential form. And the Fisher metric can be written in this form, but of course these information geometric structure coincides because this is just a change of local coordinate. So this is just a coordinate change of Fisher metric. So one exponential family, when one exponential family, if we change random values by matrix and parallel transport, so affine coordinate change, then random variables and normalization with respect to random variable change like this. So if we consider an exponential family of E form, then and if the normalization function is linearly dependent to random variables f sub 1 to f sub n, then this exponential family can be written in pure exponential form. Okay, so so next, let us consider deformed exponential case. So let chi be a non-decreasing function. We call chi a deformation function. Then chi exponential function can be defined by the solution of this nonlinear ODE with initial condition equals C. So usually this initial condition are given by x 0 equals 1, but this is just the initial condition, so we can change arbitrarily. So if initial condition C equals 1, we omit the initial condition and we write deformed exponential like this. So this is Q exponential case. So if we change initial condition, the Q exponential change like this. So if so deformation function is a power function, in this case we obtain Q exponential function in Thalys statistics. But if we consider the initial condition equals 0, then this deformed exponential function can be written in this form. So this is called alpha representation or alpha embedding in information geometry. So if we change initial condition, so alpha representation is recovered. But deformed exponential function may not be defined entire alpha, so we often consider rectified deformed exponential function like this one. So we use cutoff function. And in particular, if the deformation function is constant and initial condition set 0, so 0, exponential function is the cutoff function itself. So it is well known as rectified linear unit ReLU in deep learning theory. So anyway, deformed exponential function can be described these class of functions. So this is a definition of deformed exponential function, and just we say that a set of probability densities is a chi-C exponential family or deformed exponential family if it is defined by this pure exponential form. Okay, so this is well-known result, but student T distribution or Q Gaussian distribution is a Q exponential family. And if we consider a discrete set, then the set of probability density on discrete set always chi-C deformed exponential family like this. So okay, let us consider the geometric structure, but we need escort distribution. So using a deformation function, we can define escort distribution and normalized escort distribution like this. Then we consider expectation with respect to the escort distribution. And since we have a potential function, we can define some deformed Fisher metric and deformed Amari tensor field. Then in that case, we obtain dual flat structure like this. So this result is almost same as in previous GSI talk, but if we change initial condition, this statement holds. So deformed exponential family is a dual flat space, and natural parameter is an affine coordinate system. And Hessian normalization function is a Riemannian metric. And escort expectation that
Hessian is positive definite. In other terms, why psi is convex is not correct?
No, precisely we need assumption. Usually, normalization function is semi-positive definite. So we need we assume psi is positive definite, but it is same as in ordinary exponential case. Even if we consider ordinary exponential case, we have to assume normalization is positive definite, strictly convex. So and okay, so this is a negative entropy, but negative entropy determines the dual potential of deformed Fisher metric. So let us skip the divergence. And next, let us consider normalization problem for deformed exponential family. So normalization of positive measure to probability density is not a trivial problem. So a function f is called E normalizable or exponential normalizable if there exists a function psi theta if total integral equals 1 and this function must be non-negative. And this function is called M normalizable or mixture normalizable if total integral is finite and this function must be positive. So in both cases, these functions determine the probability density on the sample space, but the properties are completely different. So these are two examples, but let us consider ReLU case. So for final sample space, let us consider the set of probability densities. Then if we consider exponential normalization, then new probability density can be written in this form. So E normalization using ReLU is just a parallel transport based on some point eta 0. But if we consider mixture normalization, then the answer is like this. So this procedure is that the all probability smaller than eta 0 makes 0. So this normalization may also be useful of parameter reduction, but I don't know further result. Okay, time is over. So this is conclusions. So we consider initial condition of deformed exponential function. Then we can describe some alpha representation in information geometry or rectified linear unit. And this condition affects the normalization of statistical models. Okay, thank you.
Any questions?
On slide 14, I guess, you mentioned it, generalized, this one, generalized relative entropy.
Yeah.
So what do you mean exactly by generalized this because you can replace the functions by the deformed ones? Because this seems to be still related to the Shannon entropy, right?
Shannon entropy we consider ordinary logarithm and ordinary expectation. So just we change the deformed expectation. So we call it generalized relative entropy. But we obtain many kind of generalized relative entropy because
you can reduce, for example, for Renyi one or.
Renyi is kind of different, but Taris or Kaniadakis and so. Yeah.
They reduce to that.
Yeah.
Thanks.
There are questions? If not, good talk. See you guys.
Thank you.